Hi, this is Cross and Nabla, and this is our final video in Chapter 11 for Calculus 3. And today we're going to be covering over curvature and normal vectors. In our previous video for section 11.8, we discussed how to find the unit tangent vector, which we just called t is equal to r prime of t over the magnitude of r prime of t, like this. And it's just like any other unit vector, but in this case, the tangent unit vector is going to help us describe the shapes of curves, and also the direction of which these shapes of curves are changing, right? And in this section, the two main things we're going to be covering are curvature and normal vectors. And curvature just represents how fast a curve turns at a point. Fast a curve turns at a point, and then normal vector describes the direction in which a curve turns. So for curvature, I think the best example for real life application would be for a car, right? Imagine driving a car along a winding mountain road. There are two ways to change the velocity of the car or to accelerate. You can change the speed, or you can change the direction of the car. A change of speed is relatively easy to describe because you just go faster or slower, right? It's kind of obvious. Like, for example, if I have something going this fast in this amount of time, let's just say t, versus this in this amount of time, t, we obviously know which one's faster, right? It's going to be the second one. But a change of direction is more difficult to describe because it's not just going faster or slower. That's something we can intuit pretty easily in our head. We look at the change of direction, right? So, for example, if your car is going like this, then it has to go like this. Change lanes. You want to go on the left lane on the highway, for example. You want to go faster. That's you're changing the direction of the car, i.e. changing your curvature. Or you're going on the highway. Let's just say you have a highway like this, and you're bending over because you're by like a hill, or you're by like the mountainside or whatever, the edge of the mountain, right? You're going straight, and then you have to curve across. That's what we would describe curvature as, being the rate of change of the car changing its direction, right? Yeah. And t in this case, and t in this entire video is just going to represent the unit tangent vector, in which, when we know about unit tangent vectors, that it's always tangential to the actual curve. So it'll be like this at this point. It'll be like this at this point. I should use red instead because that's what the color it is supposed to be. But you get the idea of the unit tangent vector. This is something we covered in our last video, and this is in section 11.8. And in this case, we can see the change in t as we move along the curve, a small increment in arc length, delta s. So we call our arc length s. So a small change in s can result in a very large change in the direction of t. How much does the unit tangent vector change over that small change in t? As you can see right here, for example, this point to this point, a small change in your arc length slightly increasing, gets you a way different unit tangent vector, as opposed to this one right here, where it's relatively flat and, in fact, quite linear. So in this case, we would say that this curve on this interval has a greater curvature than this curve on this interval right here, right? And you can think of that as a type of acceleration along the curve, but it's actually something a little bit different because it's not referring to the change in your distance. It's referring to the change in your arc length. It's generalizing that to all curves. And we have the definition right here, where we have R describing a smooth parametrized curve. If S denotes arc length and T denotes R prime over the magnitude of R prime, just a unit tangent vector, the curvature of K, or kappa, of S, is a function of S, equal to this. And this makes sense if we go back to our earlier example. The small change in S for T, it's like dT/ds, and it's kind of it's kind of like if you were to do delta s, the limit as delta s approaches 0, that's another type of derivative, right? And that's a pretty cool application of this. And if you actually break this all down, we know that v equals r prime. We can just set it up like this. And this is what you would get for your curvature, or kappa. Kappa is usually the symbol you would use for curvature. In this example, lines are never going to have curvature, right? Because in order for something to have curvature, it has to change the direction of the unit tangent vector. And in this case, is kind of trivial. We can just show it for ourselves. We know that t equals r prime of t over the magnitude of r prime of t. I always like to write it out just in case I forget. And then we have r prime equal to a, b, c. The magnitude of r prime is equal to a squared plus b squared plus c squared. And then we have this, and then you have to do r prime over r, magnitude of r prime of t, which you get a, b, c over this whole quantity. You take the derivative of that with respect to t. All these are constants right here, so we can just say that the curvature is going to be 0 for all points on the line. Circles have constant curvature, for example, 3. This is just invoking the same idea that we were talking about earlier. You can try this example on your own. Feel free to pause the video to show that the curvature of a circle, kappa, is always going to equal 1 over r, and r just refers to the radius of the circle. All right, let's jump into it. So r prime is just negative r sine t, r cos t, and the magnitude of r prime equals r. So then we're going to get negative sine t cosine t. Because the r's are constants, you can pull them both out of here and here. And then you can divide that by the magnitude of r prime of t. You need to take the magnitude of this as well, which gets you to just be 1 over r. That's your kappa. And if you think about this for a circle, right? If we draw a circle out, the larger your circle is, in fact, the less curvature it's going to have. Like, for example, if I have it like small like this, give me a smaller change of the arc length, to a bigger change in your unit tangent vector, right? Because if you think about it, if you have it be like 0.0, like 0.01 versus like 100 for your radius, you go a tiny bit more, a tiny change in your t along the circumference of the circle. You're gonna have a way different value than if you go like a tiny change for 100 for a circle with 100 units as its radius, right? It's gonna be way different. And you can see that right here. I'll just put this in green, it's gonna be easier to visualize. Tiny changes like this, but a tiny change on a circle like this is much smaller. It's essentially the same. It's essentially just a line, and that's the idea we talked about in Calculus 1, where you zoom in enough on a specific function or a specific value, it's going to just appear as a straight line, right? And in this case, for circles at large radii, that will appear to be the case. Yeah, and then there's an alternate curvature formula, which is taking a long derivation, which you can do, but it is kind of tedious. But this is the definition of it. It's a pretty elegant derivation, but I will not be showing it in this video today. And for example 4, we want to show the curvature of the parabola for this. And you can feel free to pause the video. If you've been watching the series, you've gone over the cross product video. Shouldn't be too terrible to solve for the cross product of A and V. All right, let's jump into it. So V equals 1 to AT, A equals 0 to A. But we also have to not forget that it's going to be, it's going to be comma 0 for both of these. So it's going to be I, J, K, 1 to AT, 0, 0 to A, 0. Cover your left finger on the I hat. 0, 0 also cancels out. 0 I hat minus, not 0 J hat. Is your 0 J hat? It is. And then K hat is going to be plus 2A K hat. So then we have 2A over the magnitude of V squared. Oh no, magnitude of V cubed, excuse me. So it's going to be square root of 1 plus 4A squared T squared, cube that. And that should be our answer for kappa. And let's just see where, as A gets larger and larger, as T gets larger and larger, what does the curvature of a parabola become? And this just represents y equals some like this in terms of it. So if I draw out the parabola, it's going to look more and more like a straight line. That's my prediction. So let's see. So we're going to get 2A over 1 plus, actually no, it would tend to 0 actually, because it would just become a straight line. Yeah, the curvature would actually tend to 0 because as this gets larger and larger, this is going to approach infinity. It's just going to be 2A over infinity, therefore it's going to be 0 for the curvature. Pretty cool. These are some cool examples you can try on your own. I'll kind of go over the part A example real quick. It'll be kind of straightforward to go over, but if you want to try this on your own, feel free to pause the video. All right, just go over part A and part B. Not 0, it's going to be B per okay, and then we have T equal to okay, and then we take the derivative of that. We're going to get T prime equals negative A cos T negative A sine T is 0 A squared plus B squared. You have to take the magnitude of this though, because that's what the formula wants you to use. And then you would just get A. You would get A over A squared plus B squared. You have to divide it by R prime though. The magnitude of R prime, excuse me, which you're going to get this. Which means use your exponent properties. You would just get A over A squared plus B squared. Let me move that down for a second. And that is what your kappa should end up as. Part B, we're going to do the same idea. So we're going to have V equals negative A sine T, A cos T, B, A equals negative A cos T, negative A sine T, 0, and then we just do I, J, K hat. Doesn't matter which order you do it in. It could be A cross V, V cross A. You're just taking the magnitude, right? Yeah, taking the magnitude and not really worrying about the other components. And we just got to put in our acceleration component. It's going to be negative A cos T, negative a sine t, and 0. So let's just use our right-hand rule, not our right-hand rule, our thumb rule, where we just cover over the I hat, j hat, and k hat components. So then I get negative ab sine t I hat minus ab cosine t j hat, and it's going to be two negatives here. Actually three negatives, so the two negatives make it positive times the negative, and then you're going to get plus, plus a squared k hat. And then from here, you're going to take the magnitude of this to get your result, which is just going to become a squared b squared plus a to the fourth. Take the square root of that. You can factor this component out to get a squared b squared plus 1. And then we can go back to using the v cubed definition. And if we do this, take the v cubed of everything, we're going to get a cubed. Actually, no, we're not going to get a cubed. Sorry, we're going to get a squared plus b squared this should be not a squared, this should be a, excuse me. And oh shoot, no, either this part right here should be a squared that should be a squared plus b squared times a. Yeah, that is something I should have noticed a second ago. Yeah. And then multiply this. You cube this. This goes away. This goes away, and you're just going to be left with a over a squared plus b squared as your kappa. Now going on to the second part, going over the normal vector. Essentially, the curvature describes how fast a curve turns, your change in your velocity with your change to your curve, right? The principal unit normal vector is an extension of that, where you're going to be basically seeing the change of the unit normal vector along the curve. And in that case, what will happen is that your unit normal vector for a curve, some arbitrary curve, will look like this. Your curvature measures how fast is the change in your velocity with respect to the change in your curve. Your unit normal vector goes inward and is your normal acceleration in that case. Looking at this, n is usually the way you would define it. And again, this is another way to write it. You can write it either like this or like this. Either way, it works. And you can determine the unit normal vector from that, right? Example 5 says to find the unit normal vector for the helix. And this is just taking the same process that we did earlier, where we solve for t equals r prime of t over magnitude of r prime of t, take the derivative of this, and then take it over the magnitude of the derivative, right? This is a pretty straightforward process, and yeah, so just try this on your own, feel free to pause the video. Let's get right into it. So r prime is equal to negative a sine t, a cos t, b, magnitude of r prime equals a squared plus b squared. So then you get r prime of, you're gonna get t equal to magnitude of a sine t, a cos t, b all over this entire quantity. You take the derivative of this with respect to t, you're going to get negative a cos t, negative a sine t, 0 over this. Then if you take the magnitude of this, you're just going to get a. I take the magnitude of this entire quantity, you're just going to get a. And then you're just going to, this is a constant, right? Square root of a squared plus b squared. So this is just going to cancel out. And then we're left with this whole quantity. So we're just going to bring that over here. We have a times negative cosine t, negative sine t, 0. And we can pull out the a from everything because the 0, pull out an a from 0, you're still going to have 0, right? And then you're going to divide everything by, a. And then you're just going to be left with this for your principal unit normal vector. And funnily enough, this is a result similar to centripetal acceleration. When we cover that in our curves and lines in space video, when we talked about how the second derivative of a curve of a circle in motion, it's always accelerating inward towards the center. That's the centripetal force, and this is that normal force that's normal acceleration or normal force being applied there, right? And in fact, that actually covers us to our next section of this, talking about the components of acceleration, right? So we have tangential and normal acceleration. So we talked about this a little bit above here with your unit tangent vector and your unit normal vector. They're always orthogonal to each other. In this case, it's perpendicular because they're in 2D, but it's going to be orthogonal in 3 dimensions. And you can see that the vectors t and n can describe 2 different changes of two different ways to change the velocity of an object, or to accelerate it, is to change the speed and direction. So changing the speed gets you your unit tangent vector. Changing the direction produces acceleration in the direction of n, right? So you have change in speed gets you your unit tangent vector, and then your velocity in the unit normal vector. And this is the proof that goes along with it. So we have, solving for acceleration, you have this, and this is just referring back to an alternate definition of what velocity is, right? Due to unit tangent vector times your speed. And then you take the derivative of this, you have the product rule applied. And then you have, taking the second derivative of this, you get acceleration, or you would get tangential acceleration, right? So this is your tangential acceleration, what we would normally consider acceleration, not normal, but normally consider acceleration. And taking the derivative of this, you get your velocity, and you square that with your n. This kn kind of comes back from our unit normal vector definition from above, right here. So it's going to be k, you have kappa times n equals your change in your unit tangent vector, or your change in arc length. And then that's just applied right here. And then this is what you get here for your velocity squared. And you have t times the second derivative of your position over time. And as I'm looking at this, yes, okay, yes, all right, yes. And yeah, this is what you would get. And in fact, your normal acceleration looks eerily similar to this idea that we went over in, idea you would have went over in physics 1, where you have your, this looks eerily similar to this, or v squared over r, where for circular curves, what's your kappa? It's 1 over r. That's kind of an elegant way this pops out at you for this definition for normal acceleration. And for the alternate definition of curvature, you also have this where you can just, you would have it cubed right here, you would square it, and then this should be right here. That's how you would get that result. And tangential acceleration is just this, and then you add them up and you just square the components, take the magnitude of the components to get the actual magnitude of the acceleration. And yeah. And with this, finding the components of acceleration on the circular trajectory, r of t, this is kind of the similar process. This is like a nice shortcut you can use. Since we know that our tangential acceleration is kappa v squared. V is just going to be r omega sine omega t, r omega cosine omega t, negative. And when you cube that, when you square this, you're going to get r omega, r squared omega squared, r squared omega squared, divide that by r, you get r omega squared for your normal acceleration. Your tangential acceleration, however, you have to take by solving for the second derivative of your position, the magnitude of it. So you would have to just take the derivative of this twice, and you would get negative r omega squared cosine omega t negative r sine omega t. Take the magnitude of this, you get r omega squared, but you have to take the derivative of this with respect to time, and you would get 0 as a constant. And if you're familiar with physics 1 or mechanics, classical mechanics, you would have this as a common example for conservation of energy forces being applied, right? When you're right here, the block has that centripetal force Fc equals mv squared over r equal to mg. It's pointing inward. That the acceleration of the block is going inward, and it's all normal. It's all normal to the surface, right? It's not tangential. Tangential would be going like this. There's no tangential there. It's all normal, right? And that's where that comes from. And for example 7, this is going over a driver of a car follows this parabolic trajectory through a sharp bend. Find the tangential and normal components of the acceleration of that car. Again, feel free to pause the video on this one. We have the examples, the definitions right here, and you try this on your own. For this one, I'm actually going to use the cross product definition instead, so we'll just use that. So it's going to be v in A equals 1, 2t, 0, 0, 2, 0, I, j, and k, 1, 2t, 0, 0, 2, 0. And then we can just solve for it. And then you get 2k hat as your only thing left over, because everything else is going to be going to 0. That's just how the matrix works. We can just double check though. 0 here, 0 there. 0 here, 0 there. Nothing works. 2 minus 0, right? Divide that by the magnitude of v squared. Not divide by the magnitude of v squared. Divide by the magnitude of v. And this, in fact, should actually just be 2, because we're taking the magnitude of it, right? So just 2 over magnitude of v, just 1 plus 4t squared. That's your tan acceleration. And then your normal acceleration is just going to be taking the second derivative of your position, taking the magnitude of that. So then you would have this, and you would get 4. You get 2 as your normal acceleration. And that is pretty much covering over everything with curvature. Thank you so much for watching. I hope you guys have a fantastic day. This is CrossDot and Nabla.